make sure that we're getting nice bubbles. So this is definitely a two-person job. So in a minute we're going to collect the bubbles of methane and release them into the air, and because methane is slightly less dense than air, they float, and you can light them with a stick. Now obviously this is a very technical, it's a garden cane with a paper plaster on the end, but actually it's really good for lighting things at long distance. So who wants to be the lighter? Lovely, thank you Toby. So there's a Bunsen burner over there and some splints for you. Yeah, if you want to go to that side. Oh no, okay, go over there. Alright. Yep, right, so just bubble. Just keep it a little bit out of the way from there. So all I'm going to do, and it's probably best if you've got wet hands, is just collect some bubbles off the top there, push them off, oops, and then if you like them. Cool. Yeah, quite nice. Does anybody want to come and just... Right, so that's it.
The sleeve.
Okay, yep. Feel anything? They'll do it from this side. They're going to hold the rocket with their hand and take the bung out with their other hand, and they're going to take one good step back. At the same time, their friend is going to be over on this side with the lit splint, and as soon as their friend is completely out of the way, now you don't need to rush actually, the gas doesn't like fall out, but you do need to be relatively prompt. You just literally hold the lit splint in the neck of the bottle and you'll be surprised how far it goes. Now because actually it is really quite a loud bang, it's your rocket, you've got to wear ear defenders. Everybody else, and this is a Tim Harrison thing, don't put your fingers in your ears because when it goes bang, you'll shove your fingers further in your ears. So you have to put your hands over your ears like that. That's the better way to protect your ears. Okay? Right, so I think that's all the health and safety for the minute. Who's willing to go first? That was very top run. That's action, I like it.
No. That, yeah.
And stand that way. Oh, put the in quickly. I think we'll probably still do that. So just bring it down a little. So then we need a fuse to start the reaction. So this is just a piece of magnesium ribbon. You'll notice I've just given it a little coil at the bottom, so it's going to make good contact with the ignition mixture, and also it's going to stick quite steady. And so I'll have to put that into the well with the ignition mixture without messing up the iron. Okay. Right, and then you need two safety screens, one at the front, one at the back, and lots of leak-proof mats. Okay. Now, you might be aware, whereas back in the day you could watch magnesium burn with just your eyes, these days you have to use, students are advised to use grade well 9 grade, welding lenses. So if I can pass these round, can you just take out a welding lens to watch the reaction through? And if anything like students, you're going to. And hopefully, if all goes to plan, we will generate a molten iron which will drip into the pot here. If you are going to be a chemistry teacher, I strongly recommend you get a creme brulee roller because you're not faffing around with pipes or Bunsen on long pipes that could knock them. It's so much easier if you've got the brakes. Right, so you can see here that we got the molten magnesium and it dropped into the container at the bottom. But the slight downside of this magnesium, it's quite hard to actually see the magnesium. I could in a minute dip in with a magnet, but I wanted to just show you the alternative method, which I think is a little bit more so. So the alternative method is this one here, which is the beads method. And what this does, this uses two terracotta pots that have got a good sized hole in the bottom. So be careful, when you buy them off Amazon, they can come with quite a small hole in the bottom. You actually want them with really quite a significant hole in the bottom. You look on the Creeps SRA, they tell you there's like a traditional pottery in Derbyshire where you can buy them from, and actually it's quite nice to support them. So you get a little bit of filter paper and you just put it over the hole so that it's not, the thermite mixture is not all going to come through. And whereas the one over here, we do it with 3 grams of aluminium and 11 grams of iron oxide, this one, we do it essentially with 3 or 4 times the scale. So 11 grams of aluminium and 32 grams of iron oxide. Now, last session, this didn't work. The iron oxide has got to be ever so dry. So if it's a little bit damp, it stops the reaction from happening.
Is it safe to store thermite mixtures, or are they quite reactive?
You shouldn't store them made up.
Yeah.
What you should do is put the aluminium and the iron oxide in the oven separately, dry out, and then mix them when you're ready to use them. Again, you can set it up like a break. So, I'm going to put it into the pot here. And you have 2 because invariably the inside of one cracks with the reaction. And then I need to put my ignition mixture and my fuse into it. So, now, what's nice about this is the molten iron, in theory, generates a thread and it falls out, and you can see it kind of molten metal running down. And you might have seen that they use the thermite reaction to weld train tracks together. So once you've done it on either of these scales, you can then just find a video that shows rail track, British Rail employees using the same reaction, and the molten iron is placed between the 2 train tracks and it wants them to. So, let's put this in there. amazing because it properly drops it at the bottom. So I might set it up with a sparkler and see if we can just get it to go with a sparkler.
So what's the benefit if you use this one?
The benefit is it's larger, and the benefit is that the molten iron drops at the bottom here, which means that then you can see that lump of molten iron. So what we'll do is we're going to do that one. While you're doing that one, I'll just fiddle with this and put a sparkler in, and just see if we can really go into it. It is spectacular. Right, so if you're doing it with the sparkler, you literally just take an indoor sparkler, push it in as far as you dare, while still giving you space to light it.
How far down, like a centimeter, or?
Well, so if you have a look, it's the sparkler's that long,
Yeah.
and I've pushed it, so I've pushed it like an inch in, haven't I? Right. You will find that when you do this in your own school, you will find to get a setup that works perfectly. It's just really hard to do it. Right, we're ready. Fingers crossed. Have you got the welding hammer?
You good?
You good? Good. Now obviously so it's really, really hot at this point. The students can see that you've got that molten iron. If you wouldn't, because it's so red hot, but if you went near that with a magnet at the minute, it wouldn't be magnetic because it's still in the liquid space, so the mains are still flicking back and forth. So if you want to show that you've definitely made iron, you do have to wait for it to cool down and use the magnet. And then if you did that, let's say at the start of the lesson, by the end of the lesson, it's cool enough that you can pass around that lump of iron that you made from the iron oxide from the hematite. So please we went back in that. So if you want to wash hands, go and get some lunch, and then have you done microscope?
Yeah.
So then that session is in there. If you want to leave your lab coat somewhere in here, that's probably easiest. And if you could bring me back the welding lenses, we'll just make sure. And just stir them, okay? And it's really unusual. So it starts off, it's just like you're stirring two solids, but already I'm down to 15 degrees C. So it started off at about 20 about room temperature. And just keep stirring. And it's going to get a little bit slushy. And the temperature's now down to 9 degrees C. And if you know, if you've got doing it in your school and you've got data box, this is perfect to have it with a thermometer and it projected on the screen behind you. And it's now down to -8 degrees C. And you can see how it goes into this funny slushy paste, really odd reaction. And the only downside of it is that you might be able to begin to smell it, produces ammonia. So only do it as a demonstration, you wouldn't want to do it as a whole class because otherwise, you know, they're really smelly bad. And we're down to -18, because the thermometer only goes down to -20 until the technician. So we've got to -21 now. Now, the thing is, you've generated enough cold that it's beginning to freeze the water and it sticks. So if we leave that a little bit longer, all of that water will freeze and it sticks to the container to the Petri dish. So it's quite a nice visual demonstration, but I think it would be even better if you could have it on the baseline. It's an exothermic one, and it's the same reaction as you use in hand warmers. So does anybody know the chemical in hand warmer that when you click it freezes? Anybody know what it is? So it's sodium acetate. So what we've got here is in each of these little shot glasses, this morning I came up and you take 125 grams of sodium acetate trihydrate and you add just 12.5 centimetres cubed of water and you heat it up and it melts dissolve. I wouldn't like to say that it's melting or dissolving, but essentially what you're doing is making a supersaturated solution, which is what was in the handballs. You then take, so I'll demonstrate with this one, which you can see there. So when you're ready, and again you're going to do it in your groups of, when you've got 1, 2, 3, 4, yeah, these 4, so again in your groups of 3, you're going to very, very carefully move the shot glass from where it is to where you want to do it. If you shake, this happens, it crystallises in the shot glass. So this was one of the groups that did. You then take with a spatula, in these different coloured shot glasses are just the undissolved sodium acetate. So you can literally just put a little sprinkling of the crystals and they act as the site of nucleation. And then very, very gently you pour the solution and you should be able to make a stalagmite of sodium acetate. Now the last group, they were insistent they wanted to measure them, so we got as high as 16 centimetres. So the challenge is, can anybody beat 16 centimetres? Okay? So choose your pot of the 4 that are around the side. Off you go.
Now it's going.
Oh, it's going. Yours is going already.
Oh no. Oh.
Now this is one that you do have to.
I think it's because of the vibration.
Yeah,
on the bench. Yeah.
There's a few left.
No, they're for the afternoon session.
Pour it.
Pour it really gently.
Can we heat it up again to get back into it?
You could, but it's in a plastic thing. And actually, it takes quite a long time. It took like an hour to dissolve all this morning. Yeah, so that's useful. Excellent. Quick, pour it. Okay, go on. Can you pour it over?
We got 16 millimeters.
Let's go.
It's gone, yeah.
Can you explain how you prepare it?
Oh, so good. Keep going. Oh my gosh, we lost.
So it's quite a nice competition for students actually. Don't go too close because otherwise it crystallises back into the container. Very good.
Suspense.
Thank you.
Is that it?
So again, quite a nice demonstration for the students. We did it by the Scottish, so the Scottish version of clips is called CERC. And so what we've got here is 100 volt hydrogen peroxide, so you need nice concentrated hydrogen peroxide. And because last session it overflowed, I'm doing it in a bigger container, but because I want you to be able to see and the students to be able to see, I want to raise it up so that it's not panicking. And do 200 mils of hydrogen peroxide in a 500 ml measuring cylinder. Okay. You will find that some schools do it in pop bottles. Now I always think I'm a bit worried with those because the gas is produced so quickly in the bubbles, it can spray out, which means you've got hydrogen peroxide spraying at places. So I much prefer to do it in something with quite a nice wide neck so that it's that little bit more controlled. And then to trap the bubbles, we need the detergent, so I'm just going to add some detergent. And then because it's called elephant's toothpaste, you can, if you want, add sort of food colouring. Now, if your food colouring is kind of like liquid, it runs down the side, so I prefer to use gel food colouring. So you put a nice blob of the food colouring at the top.
Can I ask when you'd use this practical? Like which parts of the syllabus you use?
Yeah, so where's Gordon? When did you use it?
I did it kind of for fun. So you were off the back of balancing equations, starting to think about chemical reactions.
Yeah.
And it was just like did a number of videos to show you can take elements and mix them together. You can do more complicated stuff. And they saw a gift of this, and they're like, we have to do it. I was like, we're going to do it. So.
Where you can do it in the curriculum is it's catalysis. So you're speeding up the decomposition of hydrogen peroxide. You could use the manganese oxide catalyst, which is what we use over there for the generating oxygen. Or in this case, we're using potassium iodide catalyst. And actually, there's a past practical way you can do where they use 20-volt hydrogen peroxide and they add different metal oxides to find which is the best catalyst, and then you do it on a bigger scale based on their results. So that's quite nice. So for this one, if you use 200 mil of hydrogen peroxide, 4.5 grams of potassium iodide is probably the best amount. And so we're just going to watch what happens. You just literally look at it. And it's one of those reactions that starts off quite slow, and then now it looks like it's brown because it's producing iodine. Just keeps going, and you
How
can
long
see
did it
it's
take to clean it up?
Technician,
Technicians
they weren't happy. Mine went forward through.
So, but you can see how we've got it on some bin bags, so that if it does spill over, in fact, all the technicians need to do is just kind of swoop it up into the bin bag. The other quite nice thing with it that you can do, depending on whether it wants to play ball or not, is because you're turning the hydrogen peroxide into water and oxygen, you can show that you're making oxygen because you should be able to relight a glowing splint in the bubbles. The problem is that the other product of the reaction is water, which obviously puts out the fire, so it can be a little bit, sometimes it works, sometimes not. So you blow it out. See how it relights, a little bit much. Yeah, so you can keep going that much. So that's the elephant's toothpaste, which I'm glad you asked the question about when would you do that, because actually it's really nice.